okay, like I said, I was like, I'm not PTA, so I have no idea what's going to be on the postage stamp. So like, if I don't cover something, I'm screwed too. So I really don't want to be held accountable and be like, you didn't teach this, so, and I failed the exam, so it's your fault. And I'm like
someone really loved you and was like,
no.
Oh, you didn't like.
I mean, there's 100 people in that group chat, so
Yeah,
who knows? There could be, I don't know. Pretty much just like your own responsibility. Make sure you're prepared for the exam. The thing is like, yeah, I do this shit too. We're like, oh, I just want the answers to the homework because I'm lazy, or I don't really know and I don't want to go through the work of trying to figure it out. You're gonna screw yourself because what's on the homework is gonna be on the exam, and like doing the extra practice that's gonna help you. Like knowing what's on the exam, yeah, but if you practice what you think is gonna be on the exam, it's like doing math. Like if you don't practice math like questions, and you're gonna fail.
I did all the homework and I saved it or took a picture or something, and I was like, someone's this damn homework. I was literally buying that girl.
Yeah, like I said, like the only benefit you would get from getting the answers is to check yourself.
Yeah, and the the points. Like that, I only wanted like the points. Like we get one.
Yeah, and that's what I do. Like I'll be like, okay, I think this is it, and then I'll look at the answer.
Sweet.
But like just going through and like picking it's not worth it, you know. Yeah, okay. Do you guys know all the polyatomics or someone? I don't know if he's going to give you the polyatomics or if he's going to say, so-and-so, there's 3.2 grams of ammonium, but he doesn't give you this. Well, if you have to find the molecular mass of this and you don't know what the formula is, you're so screwed. Like you're done already there. So I recommend making like a Quizlet or something of like, I literally pulled this off his slide. So I have a huge one, like in my notes from when I did my other class, and it is like, these are all the ones I have now, and it's like 2 rows all the way down. And he's like, oh, you should have learned this in Gen Chem 1. And I'm like, we all have different professors for Gen Chem 1. I don't know this. So I will learn those, just to be safe. Or at least the basics like nitrite, nitrate, stuff like that. Okay, so the first stuff that he went over were in intermolecular forces. People say IMF, I say IMF. Pretty much dumbed down. So it's called London dispersion. You call it dispersion. That's why I call it dispersion. It's all molecules, and it's all compounds. It could be just one element, or it could be multiple elements together. Because really, it's just the forces between the center of the atom and the electrons. And all atoms have that, right? The second one is dipole-dipole, only polar molecules. So water, for example, is polar, correct? Well, actually, let's back up. Do we know the difference between polar and not polar? Sort of? Or yes? No, like, seriously, if you don't know something, like, don't be afraid, because I can add, like, that's me, like, I didn't know the basic shit, because I could have just skipped out on it, and then I was screwed. So, like, it's better to know and ask the basic shit now than, like, 2 months. Yeah, I can go, yeah.
I just don't know how to find which ones are. Like, I know what they are, but I don't know how to.
Like, how to identify it?
Yeah, which
Like, if somebody gave you, like C, like carbon, Cl4, right? And they're like, is that polar or not polar? Is that what you're asking?
Yeah. Like
So, I'm a visual person. So, I'll draw this out, right, in the Lewis-Scott structure. So, like, Cl would be the central atom, right? And then you have 4 Cl. And then for the Lewis-Dot, you have to put the electrons,
So
right?
it's all
It's non-polar.
Wait, how do you know it's not polar?
So Lewis dot structure, valence electron has to be 8 for most elements, correct? So I'm just drawing it. This is full, right? Well, there's 3 lone pairs on each one, but it's equal all the way around, right? So like, he draws this little symbol, I don't even know what it's called, but it kind of looks like that, right? And it's like negative, right? It's negative or positive. Hydrogen would be positive, anything else would be negative because the electrons are negative. But there's equal distribution all the way around, so it's non-polar. So this is non-polar, but this, so like H2O, water, is a polar substance. So oxygen, 2 hydrogen. Hydrogen is full with 2 electrons, right? But there's a lone pair here. This, that's positive, right? And this is negative. So that's what makes it polar. You see the diagrams where it's like a big bubble, and it's like, this is kind of red up here, and then it's blue down here. That's what it means, like it's an unequal distribution of charges.
Oh, so there's an unequal distribution charge that is polar.
That is polar.
And what were you saying, like hydrogen is always going to be positive? That
Like-
makes it positive?
Yeah, so there's no electrons, right? So it's automatic. If there's no electrons, there's no negativity, which makes it positive, right? Is that clear?
Yeah.
Okay.
But if it's anything else besides hydrogen, it would be negative.
Yeah, because like hydrogen is special and it only needs 2 electrons to make it full, to make the shell full. Everything else, except like a couple elements that I don't know what they are, don't require, like they all require 8 electrons to fill that shell, right? In this basic sense.
Yeah, and so like the dipolar is just like how they're arranged, like, so they would like go around, I don't know how.
Yeah, so like when it says like dipole, and he's talking about like permanent dipole and not, like permanent dipole is hydrogen, right? Like when you're like doing like, you see like the atom and it's like this, but then it's like that, and it's like that, and these are electrons, right? Well, these electrons aren't in the same place they're moving.
Yeah.
So it changes, the polarity changes, and that's what he's talking about, permanent dipole and not permanent dipole. That's what he's talking about.
So what would permanent dipole is like when it's in the same place or
Yeah.
and temporary dipole is like it moving.
Yes. Yes. I'm pretty sure you have it. Any more questions about polar and non-polar? Everybody good? So next one is hydrogen bonding. Super easy, only between nitrogen, oxygen, and fluorine. But I'm gonna trick you in these later examples. It has to be connected, like it has to be bonded to the nitrogen, oxygen, or fluorine. If there's a hydrogen and a fluorine, but there's a carbon and oxygen, and the fluorine is connected to the oxygen, it's not hydrogen bonding, right? Because it has to be bonded to the hydrogen. And then the ion dipole is kind of like confusing at first because nobody really gives like a definition. They're like, sometimes it's this, sometimes this. Deadass is just like ionic compound. So like an example would be NaCl. And that's why it's the strongest. You won't deal with a lot of ion dipole, but that's why it's the strongest because it's an ionic bond. Like it's an actual bond. This is just forces. Like hydrogen bonding is not the bonding itself. Like when it's just like a bond or like double bond or like triple bond, that's not what this is. It's different. And the biggest thing to take away from this, the stronger the IMF, the higher the boiling point. So if I had like H2O, actually that's bad. If I have the CL4, and then I had H2O, which one has the highest boiling point? H2O. Yeah, and the CL4 only has the dispersion, right? Okay. Why are intermolecular forces in H2O gas much weaker than attractions in H2O liquid or H2O solid? Yeah. So if you look, so you know how like in a solid, right? It's like pretty packed together. It's a bad example, but it's like it's like packed together. It's a definite volume and shape. Liquid, they're kind of like they're closer together, but they're still coming around the electrons. And in gas, they're like all over the place, right? That's why because it's farther away. So the farther away the electrons are from the central atom, the weaker that bond is going to be. Same thing goes for like elements of like larger mass. It's going to have a weaker attraction on something like Se than like lithium, right? Because lithium has a smaller molecular mass, right? Yes. Seriously, if you don't understand something I'm saying, or you need me to clarify or keep going, please let me know. Because I don't know if this makes sense. It makes sense to me, but it's about you guys, right? Okay, what about, consider the following. Br2, Ne, HCl, and N2, which has the largest dispersion force. So my big thing is like looking at that, it's hard to visualize like the electrons and their shape. So I draw them out every single time. So okay. So like Br. Because if it's the same thing, why would it have lone pairs if it can bond be identical, right?
Oh. Yeah.
Like, where is Br? 7, right? It's in group 7. It's identical, which means that it can share the same electrons. I don't know, like, deeply why. I just know that that's what it looks like.
Okay.
If it's a diatomic molecule, it's going to bond like that. And that's why they're so hard to pull apart, too. So, if the molecular mass of this 159, the molecular mass of this is 28. And honestly, this doesn't matter. Even if it was, if I'm wrong, and even if it was like had the pairs, it doesn't matter, it still has the same molecular mass, right? We know how I got that, right?
The molecular mass?
Yes. Okay.
Isn't that just like you find it on there?
Yeah, so we just add it up, but since there's 2, I'm going to multiply by 2.
You're multiplied by 2.
Right. So which one has the largest dispersion force? Br2. Because
Because it's high.
it's larger. Oh, I got everything. Okay, so out of those, which one has the largest dipole-dipole attraction? Knowing what dipole-dipole is.
There's the
Yes, it's the only one. Out of all those, HCl is the only polar one. So, out of these, which of the following molecules would exhibit hydrogen bonding? Methane, I don't even know how to say hydrazine, methylfluorine, or hydrogen fluoride. So what should I do first? Just looking at this.
draw it up.
Draw it out. So, CH4. I'm pretty sure this is how you draw hydrazine. Not 100%. Not 100%. This is a border. Bottom me.
Obviously, this has hydrogen. On each end. Has hydrogen.
Oh, yeah. Just kidding. That's why I was like, I'm not sure if this is right. Okay, now answer the question. Right. Because, like I said before, just because this hydrogen and fluorine are on in the same molecule, doesn't matter. Because the fluorine is bonded to the carbon, not the hydrogen, so there's no hydrogen bonding.
Will there ever be an instance where like it would have like H and like one at the end of an F and then like C in it, but it would be bonded to
Like,
yeah.
I don't know what you're saying. Yes, it would still be hydrogen bond because there's still a bond. Just because it's like on one, but this is not real. But say this is like H, but this is like a C, right?
Yeah.
That's still hydrogen bonding.
So but that one wouldn't be like the other.
This is not hydrogen, like the intermolecular force between this, no, this is not hydrogen bonding. But the intermolecular force between this is, because there could be multiple IMFs in a molecule, right?
Yeah.
I don't think that exists.
Kind of if I ever were to come across something. Like
Yeah, yeah. But don't quote me on that. Pretty sure, pretty sure. Pretty much what we said, hydrogen forms hydrogen bonds, methylfluorine does not have hydrogen bonds, because H has no bond. So, I want you guys to tell me the IMFs present in HBr. Go. Somebody just say it. Dispersion, okay? What about I2? CO2, which it was there earlier. You're getting somewhere. H2O, dipole, and hydrogen bonding, and dispersion. CH2, Cl2. I don't know either. What about NaCl?
How can you tell just by like looking at them? Like, you know?
You can't.
Okay, I was gonna say.
You have to draw it out.
Okay, I'm like, everyone's answering these fast and I'm like.
I mean, like for me, just, and for certain people, like you could say it, but like, that doesn't mean you
It's
can.
just because I saw it before.
Yeah,
Oh,
if you
I
can
was like,
visualize
what?
in your head, okay, so here's like a hydrogen, here's bromine, and like I can look at like, okay, so here are the electrons, and it's more negative over here, but not positive. Okay, now it's dipole dipole. But really, you should just draw it out,
Okay.
just to be safe.
I thought I was missing something.
No, no. I would draw it out. That is what I do. But I know the answers to these because I made this. I just didn't draw these out because ain't nobody got time for that right now. Right? Everything makes sense. We understand INFs now. Any questions? At all? We need time to write this down. Yes, no, maybe so. I'm gonna take your silence as a no. Electronegativity. Here's a chart. He's like, what did he say that we could have this for or he was gonna provide one?
I think you said that.
Well, yeah, I think so. If you're just looking at a periodic table and you don't need to know the values, which I've never had to know the values, but whatever he wants to do, literally it's like electronegativity increases going towards hydrogen, like up and towards hydrogen, right? I mean, not hydrogen, helium. Sorry, wrong way. So towards helium, like this way, and up. It's kind of like 3D, so that's cool. I looked this up.
Where's the heat?
Yeah, see that?
Oh, it's not on there for some reason.
It's not on there.
No, it's not. Like I said, I took this off his PowerPoint. I looked this up because I was like, how does electronegativity correspond with boiling point? Apparently, the smaller the difference between electronegativity values is disproportionate to the boiling point. So like, if it's higher, it's going to be lower, right? So the smaller difference, higher boiling point. Why? Because since the electrons are closer to the center of the atom, the bond is stronger, thus creating a smaller atomic radius. This needs more energy to break bonds. Hence, a higher boiling point, right? So like, and if you did like, I don't know, like, you wanted to compare like, say like it was aluminum and carbon. Well, you would subtract the 2.5 by the 1.5. And then that's whatever value it is. Let's say like you did lithium and beryllium. But like the difference between that is bigger, so what did I say? Aluminum carbon, than that one, the other one. The smaller one has a higher boiling point. Make sense? I'm not 100% like solid on electronegativity because I never had to do this when I did Chem 2. We just had to know which direction, like the trends. So I would personally look into that kind of more. He might go over some of it like before the exam. Who knows? I don't know. Maybe he'll be cool and like do a study guide. Probably not. But I don't know. Okay, solutions, which is like the big part that we're going into right now. Okay, do we know the difference between a solute, solvent, and solution?
I don't, like, honestly. I remember
So-
not writing that one, but we touched on it.
So like, okay. Solute is whatever is being dissolved in the solution, right? Okay, so the solution is both of it together, right? We both know that. It's whatever. Water, sugar, water, salt, water, whatever. It doesn't have to be water, but that's the easiest example.
So the solvent is what it's being dissolved in.
Yes, it is most of, have you ever heard of water as the universal solvent?
Oh,
And, but really, like, I don't know if it is, because, like, it's polar, so how, he was talking about how, like dissolves in like, so you can't put a non-polar substance and try to dissolve it in polar. That's like trying to put oil in water and trying to like, dissolve it. No. So, I don't know, but like dissolves in like, polar has to be with polar, non-polar has to be with non-polar. So the solute, so let me give this an example. In sugar water, what is the solute?
Sure.
What's the solvent? What's the solution? Yeah. Simple syrup.
Wait, what did you say?
Simple syrup. That's just the bartender term.
Oh my God, are you a bartender?
Yeah.
Oh my God, me too. In Texas, you can
I'm
be
from
on.
Texas.
Yes. Okay, where?
Like,
Okay, where do you? Have you ever heard of Breadwinners? I know you
Yeah.
have. I work at Quarter Bar.
I work at Fleming's Prime Steakhouse.
OMG,
I shop
guys.
Fleming's.
We're gonna like fangirl about bartending here. Yes, simple sugar, simple syrup. That's funny. Okay, so in a solution involving solvents and solutes, there's like 3 classifications: unsaturated, saturated, and supersaturated. As in the examples up here and the definitions I wrote up here. Unsaturated, you just put like what, a teaspoon of sugar in like a liter of water. It's going to dissolve easier because there's more particles of, or mass, or whatever you want to say, of the solvent than the solute. So it's going to dissolve, right? Saturated would be there's an equal amount of solute versus solvent. In supersaturated, there's more solvent than solute. And so I think there's a lab, or at least I did a lab, where like you have to do unsaturated, saturated, supersaturated, and you have to heat whatever it is to get it to dissolve. That's what I was talking about, how you have to heat it in order to not see the sugar, but when it cools down, you see a participant, right? That's all it means. There's just too much in there. And like, if you think about how sugar bonds with a hydrogen atom, there's too many sugars. Like, there's not any left. It's all used. It's like the limiting reactant. That's how I feel. There's not enough. There's too much sugar. Yes? We cool on that? Okay. So, there are some equations that you need to know. A lot, actually. And yeah, all these have to be memorized. There's a lot of formulas you have to memorize in Gen 2. Like a lot.
It won't be on the exam.
No, probably not. I would not bet on it because I would not at all. And like it gets way worse. Like way worse. This shit's easy. So the first one is molarity, right? That is ugly. Which is a capital M, which equals moles over liters. What is a solvent normally measured in? Volume, right? What's volume measured in? Milliliters, liters, whatever, right? So clearly the solvent's going to be at the bottom, like the denominator. Okay? I mean, I could write solute, solvent, whatever. You can write that. I don't need it. Molality, which I'll call it molal. And most professors will just say molal. It's dumb. Why? They use molal as molarity. It's like, they only have like a limited number of alphabet letters they can use in chemistry, and it's like M and K. M and K, that's it. Here's a whole other alphabet, and it pisses me off. I'm like, y'all confusing as shit. So Molal, same thing. Well, this is a lowercase m. Don't get it confused with mass. Moles over kilograms. Next one is mole fraction. Which is like this weird looking X thing, which will come up later. It's like a, yeah, it's got like a little curly thing on the top. And that's moles of whatever component you're looking for. Over the total moles. AE, this moles in solution. Oh yeah. But then he says weight percent. I hear as mass percent. Weight, mass, same thing, right? So you could write it either way. I say mass, but we can all say weight too. Mass percent. Grams of whatever component you're looking for over the total. Or the solution. Also, something I added today, dilution, M1, we all know this, M1, B1 equals M2, B2, or it looks familiar at least. Okay? You guys need a second to write those down? Or do we already have?
You also said that we have to like have all this memorized.
Yes. I will memorize.
So he's not.
Yeah. No. Oh, I forgot this last one. This is not one. I know. Oh my gosh. It doesn't matter. It's just this weird looking X thing that's gigantic.